In 2010, researchers stumbled on a piece of malicious software that didn't look like anything they had seen before. It wasn't noisy ransomware demanding money, nor a data-stealing bot quietly siphoning credentials. This worm moved like a ghost through Windows machines, but its real purpose was hidden deeper. It was built to reach industrial control systems and physically sabotage machines. The name the world gave it was Stuxnet, and it quietly rewrote the rules of cyber conflict. Stuxnet didn't spread by chance, it was engineered to be invasive and surgical. It used multiple previously unknown vulnerabilities in Windows, zero-day exploits, and even carried valid digital certificates to appear legitimate. Those details alone told experts this was not the work of teenage script kiddies. This was expensive, patient, professional engineering. It spread through corporate networks, removable USB drives, and ordinary Windows computers, but its real prey was Siemens Programmable Logic Controllers, PLCs, the devices that send commands to machines in factories and power plants. The target was no ordinary plant. Stuxnet's most famous victim was Iran's Natanz uranium enrichment facility. Natanz used centrifuges, high-speed rotors that spin to separate isotopes of uranium, a delicate mechanical process requiring precise control. Damage the centrifuges and you delay a nuclear program. Conventional sanctions and espionage are one thing. What Stuxnet did was strike directly at industrial hardware using nothing more than code. Here's how it worked, in plain terms. Stuxnet first infected the IT environment, office PCs, engineers' laptops, maintenance machines. At that stage it behaved like a stealthy worm, avoiding detection and spreading to specific hosts. When it found engineering workstations communicating with Siemens Step 7 software, the environment used to program PLCs, it deployed a different layer of code. That code looked at particular PLC configurations and logic. If targets matched its fingerprint, the specific configurations used by Iranian centrifuge controllers, Stuxnet would attach itself to the control logic. Then it did something chillingly clever. It altered how the PLCs drove the centrifuges while feeding falsified data back to operators. The screens in the control room showed normal values, while the motors were being commanded to speed up and slow down in damaging cycles. Centrifuges that had operated for years without problems suddenly began to vibrate, overheat, and break apart. The deception was twofold: hide the malicious commands and hide the evidence of the sabotage. Operators saw continuity, machines were in the green. But underneath, repetitive stress and extreme RPM cycles destroyed physical hardware. That means Stuxnet bridged the gap between the digital and physical code, causing kinetic damage to machinery. It turned a computer worm into a cyber weapon. Attribution is always tricky in cyberspace, but the sophistication and scale of Stuxnet led many analysts to the same conclusion: this was probably a state-level effort. The prevailing assessment among security researchers and multiple journalists was that Stuxnet was the product of a covert program involving the United States and Israel, reportedly known as Operation Olympic Games. No government has ever publicly confirmed authorship, but the operation's characteristics, massive resources, detailed intelligence about the target environment, and a willingness to cause physical disruption, point away from criminal groups and toward nation-state actors. The aftermath was significant. Reports estimate Stuxnet ruined hundreds, some analysts say nearly 1,000, centrifuges and set Iran's enrichment timetable back by months or years. But the consequences went beyond the immediate technical damage. Stuxnet made the world suddenly aware that digital tools could be weapons of war. If a worm could cripple a nuclear program by silently changing rotor speeds, what else might be vulnerable? Power grids, water treatment plants, railway signaling, hospital equipment, all of these systems rely on industrial controllers that could, in theory, be manipulated. Another unexpected result was the malware's own leakage. Stuxnet did not remain confined to Iran. Once discovered, samples escaped into the wild. Security researchers analyzed it, wrote papers, and published details. Inevitably, bits and techniques replicated across the internet. The sophistication behind Stuxnet became a blueprint that others could learn from, raising the bar for both attackers and defenders. It forced vendors, governments, and operators to pay attention to the previously buried domain of industrial control system security, also called OT for operational technology. Stuxnet also revealed a handful of hard truths about modern infrastructure. First, air-gapped systems, networks deliberately disconnected from the internet, are not bulletproof. Stuxnet moved on USB drives, proving physical media remains a vector for compromise. Second, the human factor matters. Engineers and contractors moving between office networks and industrial environments create bridging points an attacker can exploit. Third, legacy systems are a liability. Many PLCs were designed decades ago with reliability in mind, not security, and they often run on proprietary software stacks that weren't built to resist targeted, well-funded hostile code. The public release of Stuxnet triggered debates far bigger than technology. Ethicists, international lawyers, and strategists asked if deploying a cyber weapon was an act of war. Was this a legitimate tool of national defense, a necessary alternative to kinetic strikes, or an unstable escalation that normalized digital coercion? Proponents argued that Stuxnet was a precise, lower casualty option compared to bombing a nuclear facility. Critics warned it created a precedent. Once used, others could emulate or escalate it. And emulation is exactly what happened in multiple, lesser forms. Ransomware and state-level intrusions would grow more destructive and targeted in the years that followed. On the technical front, Stuxnet's legacy is a long list of improvements in industrial security. Siemens and other vendors began hardening their products, introducing better authentication for PLC code updates and improving logging to detect anomalous commands. Utilities and industrial operators tightened operational procedures, stricter controls over removable media, segmented networks that separate IT from OT, and more rigorous patching policies. Governments set up new task forces and information sharing initiatives focused on critical infrastructure resilience. In many ways, Stuxnet pulled industrial security out of the shadows and onto the national agenda. But Stuxnet also demonstrated how messy real-world security can be. The worm's discovery came months after it had been in circulation, and part of the reason was that defenders lacked visibility into industrial processes. Monitoring and anomaly detection in factories and plants lagged far behind what existed for web servers and corporate networks. Even after the attack, patching and redesign take years. Infrastructure moves slowly, and Stuxnet's wake showed that attackers can exploit that inertia. There's also a lesson in caution. Building and deploying weapons, even digital ones, carries the risk of blowback. A sophisticated worm may behave unpredictably once it leaves a controlled playbook, and once released, code can spread in ways its creators did not anticipate. Stuxnet set that marker. Its discovery opened the door to a new era where cyber tools are part of geopolitical arsenals. New actors learned, adapted, and sometimes used the same tactics for criminal ends. The line between espionage, sabotage, and crime blurred. For those running modern industrial systems, the practical takeaways are clear. Segment networks, monitor ICS traffic for anomalies, treat removable media with suspicion, and adopt the principle of least privilege for control systems. Regular audits, simulated exercises, and collaboration with national CERTs, computer emergency response teams, are now considered baseline best practices. The Stuxnet story became a case study in how attackers combine digital stealth, intelligence about physical systems, and social engineering to achieve strategic goals. Stuxnet also forced a cultural shift among cybersecurity professionals. The discipline expanded beyond protecting desktops and servers to include pumps, valves, and rotors. Researchers who once focused on web apps started studying PLC logic and fieldbus protocols. Governments and companies invested in tabletop exercises, war gaming scenarios where digital attacks had physical consequences. The battlefield had broadened, and so had the players. Another angle worth noting is how Stuxnet changed public perception. Before Stuxnet, many people thought of hackers as pranksters or data thieves. After Stuxnet, the public, and many policymakers, saw that code could be a weapon with geopolitical impact. That shift accelerated funding for cyber commands and defensive programs worldwide and raised the profile of cyber policy in diplomatic discussions. Finally, Stuxnet's story is about ambiguity. Attribution, intent, collateral damage, these are gray areas in cyber operations. We still don't have universally agreed rules for offensive cyber action, and the international norms are still forming. What Stuxnet did show is that digital tools can deliver targeted effects with minimal human cost compared to conventional warfare, but also that the ripple effects are hard to predict and can last for years. If there's a single takeaway from Stuxnet, it's this: software can shape the physical world. A string of zeros and ones, crafted by skilled people with resources and precise intelligence, can break a machine designed to spin for years. That realization changed strategy, policy, and engineering across the globe. It taught defenders to look beyond the network perimeter and think in terms of systems that include people, software, and the physical machines that power modern life. This is CyberLens. If you found this episode useful, subscribe for more cybercrime case files that explain the tech, the history, and what it means for your digital life. ChatGPT can make mistakes. Check important info. See cookie preferences.